you remember last time at the end we were talking about channel capacity. I told you about the classical channel capacity of an IID channel anyway. And so you can define the quantum channel capacity very similarly, and it has kind of, roughly speaking, the same result. But whereas in the classical case, there was this very nice formula to calculate the channel capacity. In the quantum case, we have a formula, but it's not nearly so nice for reasons that I'll tell you. So the quantum channel capacity you can define as basically the maximum value of C such that we can send Cn qubits through through n uses of the channel with high fidelity. Meaning fidelity approaching 1 in the limit of n goes to infinity. It turns out that the classical channel capacity, you may remember, was expressed in terms of the mutual information. While you can write down that same formula for quantum mutual information, it doesn't mean the same thing classically. It has some weird properties. So it turns out that in order to talk about the quantum channel capacity, or to write down a formula for the quantum channel capacity, you want something else called the coherent information. So we're going to let E be the channel. And rho is a quantum state. Arbitrary density matrix. And so the coherent information is usually written something like this, although I think there's a few little variations. So the first thing we have to do is we have to purify rho. So we're going to add some reference system. And then we can write down this formula, which is entropy of the output of the channel applied to rho minus S of E tensor I applied to this purification. OK, so the situation we have here is this. So we have A and R, the reference system. So this is going to be psi AR. And so the state down here is rho. And we apply the channel. And so this state here is the output of the channel. So let's just call this B. And so this here, by that definition, is S of B. OK? And then we're subtracting off S of what happens if you apply E tensor I to the whole state. So that's BR here. This is still R. OK? So that's one way of understanding it. The other way of understanding it is say, well, let's purify this channel E, right? So there's some environment here. And let's call this E after the channel. And so now this is a unitary. And so that means that this global state here, RBE, is a pure state, right? And so if you have a global pure state, then S of BR is equal to S of E. So this then is then equal to S of B minus S of E. So you can kind of understand this as the kind of the coherent information that gets through the channel is the information that B has minus the information that the environment gets. OK, that's kind of an intuition for what's going on, which is kind of saying that, well, sure, information gets through the channel, but maybe it's just classical information. And the part that's quantum about it is the part that doesn't get decohered. It doesn't get kind of copied into the environment, right? Because doing a controlled knot to the environment and then measuring the environment, or just tracing over the environment, that's very similar to that. I mean, it's equivalent as a channel to decoherence. OK? So that's kind of the intuition here. And then the result is that the quantum channel capacity, actually, maybe let me call this Q, since it's the quantum capacity. Of this channel E is given by the following formula. The limit as n goes to infinity of the supremum over rho 1 over n I of, sorry, I didn't need this parentheses, of rho for E tensor n. OK, so the supremum now I'm taking over rho. So this thing here is you're imagining one use of the channel, right? And so rho is an input that has dimension equal to the input size of the one use of the channel. In this case, I'm doing E tensor n. So I'm doing n uses of the channel. And remember, I'm going to take n to infinity. And so rho is some potentially entangled state over the input for n uses of the channel, right? So it's if each use of the channel takes an input of 1 qubit, this is a 2 to the n dimensional. This rho lives in a 2 to the n dimensional Hilbert space. Okay? And it could be an arbitrary entangled state. And we want to take the best such rho. But because we're using n uses of the channel, we're going to divide by n. So if we didn't have this need for the limit, if we just so the kind of the most obvious analog to the classical result would be you'd kind of ignore, you wouldn't have all of this stuff. You just say it's equal to I of rho E tensor n, I of rho E. I guess you'd have this soup over rho still. And that would be saying that, remember that the classical formula is maximum over input distributions of I, x, y, right? And y is what you get for x through one use of the channel, right? So if we didn't have the n's here, that would be the analog. And the reason that we get this difference here is that in the classical case, if you use many uses of the channel, and then say, OK, I want to optimize x over many uses of the channel, you just get n times what you get for one use of the channel, right? And so the terminology for that is that this is an additive quantity. let me put it up here, because it's the classical one that's additive. And the quantum one is not additive. It's super additive. So and in particular, we know of cases where it's actually strictly greater. And so what that means is that while you might be able to kind of derive some code by optimizing over one use of the channel, you can do better if you're willing to put in entangled states. And this, it turns out, is closely related to the notion of degenerate codes, which is one of the various ways in which the notion of degenerate coding makes quantum error correction harder than classical error correction. OK, so the upshot of this is that you do have to take this limit as n goes to infinity. And that means that this is not really a formula that you can use to compute anything, right? I mean, you can certainly get lower bounds on the capacity by saying, well, let me look at one use of the channel, two uses of the channel, whatever, and then try to optimize the coherent information over that. The channel capacity can only get larger, can only be larger than that. But the problem is we don't really have any kind of effective bounds as to how much bigger it can get. And in particular, we don't know that going to some particular n is good enough to get within high accuracy. It could be that if you go to larger and larger n, that suddenly there's some substantial increase that kicks in. We just don't know anything about that. So in practice, this is not a formula you can use to exactly figure out the capacity. And so this is a kind of a big open question. Is there a singularity formula in terms of some other quantity? If failing that, can we calculate it in some other way or set bounds on it? OK? Yeah.
So what is the practical implication of this result?
Well, what do you consider a practical implication? I mean, I mean, it is a formula for the capacity. So that lets you figure out some stuff about the capacity. For instance, and like I said, you can certainly set a lower bound on the capacity through this. And so that's sometimes valuable. I mean, the whole notion of large-scale quantum communications is not yet a really practical thing. So it's hard to say what's practical. I mean, it also gives you a guide if you're trying to come up with codes for whatever channel. And the notion of coherent information, I should say, has somewhat wider application in terms of error-correcting codes and stuff like that. Yeah?
Just on the definition of coherent information,
Mm-hmm.
If I put in a pure state, like if rho is pure,
Yeah.
then is this 0?
No, not necessarily, because I mean, wait. Yeah. OK. Yeah. I guess it is. So the intuition here is that rho. I mean, this is not precisely correct, but as an intuition, it works, which is rho is an ensemble of possible things you could put into the channel. OK. And if you can only put in a pure state, then there's kind of, again, there's like no information there. So there's nothing to be conveyed. So this business of kind of purifying mixed states is sort of a standard trick in this and related problems. And so in this, I mean, you could maybe think of rho. Well, you have to kind of go back and forth between think of rho as an ensemble of different possible inputs, a mixed, proper mixture, and an improper mixture where you've purified it and it's part of an entangled state.
So should I think of rho as being like coming from some random-ish source, and I'm trying to get information about what the...
Yeah, you can think of it that way. I mean, in the same sense of you have this probability distribution x, it's going to, I mean, I think this will also be 0 if x is like a singleton, has only one thing. I think that's true. Because there can't be any mutual information if one of them just doesn't have any information. The thing is that these input distributions, the rho and the x, they don't exactly correspond. I mean, there's some kind of connection, but they don't correspond exactly to a code that you put into the channel to encode information. So there's a little bit of subtlety there. OK? Any other questions? OK, so the next thing I want to discuss is entanglement. So I've been talking a lot about entanglement in various ways, but how do you actually quantify entanglement, right? We have some notion. Certainly for pure states, it's easy to say this is an entangled state, this is not an entangled state, right? That's just a tensor product or not a tensor product. But first of all, what does it mean for mixed states to be entangled? And what does it mean for mixed states not to be entangled? That's a little more subtle. And suppose we have something that I've probably called a maximally entangled state. Why do I say it's a maximally entangled state? What does that mean? That means we have some amount of entanglement that's maximum. But how do you quantify entanglement? So that's what I'm going to be talking about now. It's turns out to be a much more tricky question than one would think. And over the years, many papers have been written on this subject. So I'm not going to give you more than just a taste of it. But there's some core principles and some core quantities that are worth knowing, I think. So OK. So first of all, what do we want from some quantity that we say is a measure of entanglement? Well, it should have some certain basic properties. So, and in particular, the entanglement makes sense in what's called an LOCC protocol. So we have Alice and we have Bob. And they have some quantum states. And so they're sharing quantum states. Now, if they can send quantum states back and forth between them, they can change the amount of entanglement. That's clearly going to be true, right? Could be that Alice and Bob start with no entanglement. Alice creates part of an entangled state and sends part of it to Bob. OK? But what if they cannot do that, but they can only send classical information back and forth? Locally, they can do CP maps. Alice can do a CP map on her side. Bob can do a CP map on his side. So in this scenario, because they only have classical communication, we imagine that it should not be possible to create entanglement if they didn't already have some. And it should not be possible to increase the amount of entanglement they have. OK? And that actually is kind of one of the main definitions of what entanglement is. It's something that can't be created or increased under an LOCC protocol. So LOCC stands for local operations in classical communication. So based on that, what's the definition of an entangled mixed state? Actually, what I'm going to define is an unentangled mixed state. So we say rho is separable if rho can be written in the following way: sum over I, pi, rho ai tensor rho bi. OK? So what? Yeah.
Don't you also have to impose something about the PIs? Like, it seems like I should be able to write any state like this.
Yeah. So OK. So I mean, I guess it can be explicit. So PI are probabilities. And row AI and row BI are quantum states, are density matrices. So you can always do this if you let the PI be negative numbers, or yeah, I think negative numbers is enough. If not, yeah, I'm pretty sure you don't need complex numbers in general. But if you insist that they be probabilities, that they be non-negative, then this becomes non-trivial. This is saying that this state rho can be written as a mixture of product states. OK? And so in particular, you can see that any separable state can be created from Alice and Bob, starting with just tensor product states and an LOCC protocol. So what is that protocol? So first step is Alice picks I according to this probability distribution PI. OK? And I'm assuming here that Alice and Bob know what row they're trying to get. They both know that, and they both know what this decomposition is. And so Alice then will send that to Bob. OK? And she can do that classically, because I is just a classical value. And so then Alice creates row AI, and Bob creates row BI. OK? And this, in fact, creates that state rho. OK? Does everyone see that? OK. So it's also true that if you have any state that you created via LOCC, starting from tensor product states, that state will be separable. So why is that? Well, you can think of this arbitrary LOCC protocol as suppose you write down. OK, so I guess I wasn't too explicit about this. So imagining there's multiple rounds here, right? So that Alice might do some CP map. She sends some classical information to Bob. Bob does some CP map, sends information back to Alice. Then Alice will do another CP map, including measurements, and sends classical information to Bob, and so on. And the things that they're sending back and forth are typically going to be measurement results, although that's not required in the definition, but you might as well assume that. Suppose we have some arbitrary protocol like this, and what we can do is we can write down, we can watch from the outside, and then write down everything that's sent over the classical channel. Okay? And I'm going to call that I. And so analyzing again from the outside, I can say, well, what was the probability of getting this transcript I? I'm going to call that PI. OK? And so at every step, you can analyze what Alice has, right? And conditioned on seeing a particular thing here, it's going to be in a tensor product with what Bob has, right? We can purify everything, so they're not doing CP maps anymore. They're doing pure states. And so we have a tensor product then at every step, right? And then conditioned on whatever measurement result Alice gets, she still has a tensor product state with Bob. And so what we've done is we've written the final state after this protocol in the purified form as a tensor product between Alice and Bob with probability distribution I for different tensor product states. OK? And then once we trace over the purifications, we get back this. So the upshot is that separability is closely tied to this notion of LOCC and is a sensible notion, given the rules that I set down, of what it means not to be entangled for a mixed state. Okay? And anything that's not separable is entangled, because it means you cannot create it via LOCC, starting from tensor product states. Okay, so in order to quantify entanglement, the main rule that I have to satisfy is that I need some kind of quantity that doesn't increase under LOCC. Right? That's our basic idea. And so this is called an entanglement monotone. So it's a function from quantum states to non-negative reals. And it should have the following properties. So there's going to be 3. And the third one is going to be the non-increasing one. So there's some simple ones, too. So first of all, this thing should be 0 if rho is separable. And I'm not going to insist that it be non-zero for non-separable states. But I do want it to be at least sometimes non-zero. It's kind of, I mean, there's just to rule out a trivial entanglement monotone that's always 0. And second, and this is a less trivial one, but it's pretty important. If Alice and Bob do unitaries on their side alone, that should not change the value of this monotone. Okay? So unitaries on Alice's side and unitaries on Bob's side fall under LOCC. So the third condition is going to say that it can't increase. But I also want to say that it can't decrease. Okay? And the reason for that is I want it to be truly a non-local property of the quantum state. And unitaries on Alice and Bob's sides are just changes of basis. Now, it could decrease under non-unitary CP maps on Alice's and Bob's side. Because remember, we can throw stuff away there. So as a trivial example, you have 2 copies of some entangled state. And locally, they can each throw away their half of the second copy. Right now, they only have 1 copy of this entangled state. And so presumably, the entanglement has decreased then. But if it's unitary, that doesn't happen. They haven't thrown anything away. It's just you can think of it as just a basis change. And so the monotone should stay the same. Okay? And then the third one, as I said, f of rho is non-increasing. And remember that an LOCC protocol has some probabilities involved in it, right? Because Alice can make some measurements and do things, send that result to Bob, do things differently conditioned on those measurements. And it could be that for some measurement outcomes, the entanglement does actually increase. There's protocols where that seems to happen, well, where it does happen. So what I really want to say is that it's non-increasing on average. That if I take kind of the full density matrix that I get afterwards, not conditioning on anything, then it hasn't increased. And that should be true under LOCC. And of course, if you allow things beyond LOCC, well, in particular, if you allow quantum states to be sent back and forth, in that case, the monotone can increase, right? Because under those conditions, you can create entanglement out of nothing. OK? So any function that satisfies these properties is a good candidate for being a measure of entanglement. And if it doesn't satisfy those properties, then we can rule it out. OK? Yeah.
Sorry, I may have missed this, but for point 1, why don't we impose if and only if?
Yeah, well, so that's just too restrictive. There's some interesting measures that don't have that property. So if f of rho is always non-zero for non-separable states, then it's what's called a faithful measure of entanglement. But you'll see some, including some that are clearly very interesting, that don't satisfy that property. And I'll mention that later. Any other questions? OK. So first, let's talk about how you measure entanglement for pure states. This is the easy part. So for pure state, global pure state, if it's a tensor product state, then Alice and Bob both have pure states as well. But if it's entangled, then that means that Alice and Bob have mixed states. And moreover, we know, since there's a global pure state, that the entropy of Alice's density matrix is the same as the entropy of Bob's density matrix. OK? And so this is going to be our candidate measure of entanglement. So let's see. So what I've written so far already tells you that point 1 is satisfied, right? Because if you have a separable state, a separable pure state is a tensor product state. Alice and Bob have pure states, so their entropy S of A is 0. OK? And of course, there's some entangled states where it's not 0. And it's unitarily invariant. That was one of the properties of entropy that I wrote down. Right? So we're satisfying property 2. Property property 3 is a bit more subtle. So it's a bit more subtle because, first of all, an arbitrary LOCC protocol will take a global pure state into a global mixed state. And I'm not claiming that this is a measure of entanglement for mixed states. It's not. If you have a protocol that takes pure states to pure states always, with no probability of different pure states, then that means it's a unitary on both sides. So that's kind of these two things. But there is a sense in which this is true, which is that you can say that the average amount of entanglement actually of this entanglement, this is called the entanglement entropy. Cannot increase under LOCC. Yeah. Okay. So so it turns out that you can if you're willing to make a few additional assumptions about what the measure of entanglement should look like, it turns out that the entropy is basically the unique measure of entanglement for pure states. This is the right answer. And you'll see one sense in which it's the right answer in the tutorial today, where it turns out to be the answer to an operational question of, suppose you want to change one entangled pure state to another entangled pure state, and in particular the maximally entangled state, the Bell states. This tells you at what rate you can do that. So for mixed states, it doesn't work as well. Okay. So the problem with this for mixed states, well, there's two problems. So one problem is that this is no longer true if we have a global mixed state. And so we'd have to say, well, do we want the entropy on Alice's side or the entropy on Bob's side? That seems like something kind of arbitrary that we'd have to decide. But moreover, and maybe more importantly, this property 1 is not true anymore, right? Because we can have classically correlated states that still have entropy on both sides. So for instance, if you have a classical mixture of 0, 0, and 1, 1, that has non-trivial entropy on Alice's side, which is because Alice has a mixture of 0 and 1, and actually the same entropy on Bob's side in that particular case. But that's just representing the fact that the state is not determined, right? There's classical correlation in that state, but there's no entanglement. Okay, so this is not a measure of entanglement, an entanglement monotone. Okay, so we have to look elsewhere. So before I do that, are there questions on the entanglement entropy? OK, so it turns out that for mixed states, there's no longer this notion of a unique measure of entanglement. Turns out there's many different measures of entanglement, different entanglement monotones, that all have interesting properties and all have a reasonable claim to be something useful. And they're not equal. OK, so here's one of them. So this is called the entanglement of formation. And so that's defined this way. Call it EF of rho. And so what the entanglement of formation is it's the minimum amount of entanglement you need to create the state via an LOCC protocol, right? So if it's a non-separable state, Alice and Bob can't create it via LOCC if they didn't start with any entanglement. But if they started with some entanglement, if they start with enough entanglement, then they can create anything. And so the question is, how much do they need using the best protocol, the one that uses the least amount of entanglement? So it's the minimum over pi and psi I. So pi's are, again, going to be probabilities. Psi i's are bipartite pure states of the sum over I, pi s of the entanglement entropy of this, the Yeah, the entanglement entropy of the state psi I. Okay, so psi I. So the idea is they start with probability pi. They start with the state psi I. And it may be that in order to make this in practice, they have some big bank of possible states. And so they flip a coin that determines I with probability pi, and then they go into their bank and they pick out the state psi I from the bank. And then they use that in their protocol to make the state. Okay? And so, of course, this is taken over ensembles such that rho is equal to sum over I pi psi I. Okay, so with probability pi, they pick the state psi I, and then they put that in. And because they're randomizing, they get the state. Yeah?
What do you mean by the trace of V, trace over V?
So psi I is a bipartite state of Alice and Bob. So I'm doing the partial trace over Bob's side, which is, you remember how we get a mixed state out of a good state. This thing here is just this entanglement entropy. If you want to know how to compute it, think of it as, so if you have 2 qubits, right? That's a 4 by 4 matrix. And so you break it down into 2 by 2 subblocks, where the indices in the small blocks correspond to B's value. And then you trace over all of those. And then that leaves you still with a 2 by 2 matrix, which is Alice's density matrix. Any other questions? OK, so the upshot is we have this quantity. So why is it an entanglement monotone? Well, certainly for separable state, it's 0, right? Because for separable state, they can have an ensemble that's a mixture of tensor products. And that means that they use that ensemble here, which is certainly going to be the minimum because the entropy of those tensor products is 0. So this is just sum of pi times 0. OK? So this is 0 for separable states. And if you take a pure entangled state that they want to create, well, in that case, there isn't really any ambiguity in the ensembles that you use. There's only one. You could say different probability of having that particular pure state. That's not very interesting. So basically, it's just pick that particular pure state. And so then that means that there's only one term here, and you get back the entanglement of that pure state. OK? So let's see, property 2. Well, it's clearly unitarily invariant also, because suppose you have an ensemble for rho. Well, that means that an ensemble for u rho u dagger is pi u psi I. And in particular, if u is a tensor product ua tensor ub, then the state ua tensor ub psi I will have the same entropy, entanglement entropy, as the state psi I. Okay? So we can map all the ensembles that we're minimizing over here for rho to all the ensembles for the local unitary rotated version of rho. OK? So that works too. And now property 3. So how do I know that this protocol, that this quantity is non-increasing under LOCC? Well, suppose I have some LOCC protocol that converts rho into sigma. So what I want to show is that the entanglement of formation of sigma is no more than the entanglement formation of rho. Well, here's one way to make sigma. I make rho out of some ensemble here. And then I apply the LOCC protocol to make sigma. OK? So that means that I can make sigma out of this same ensemble. And now it could be that there's other ways to make sigma that use less entanglement. And of course, there's other ways that use sigma that use more entanglement to make sigma. But this is a minimum over ensembles. And so the minimum for this has to be at least smaller. It could be equal to or smaller than the minimum for this, so the value for this particular path. OK? So this works as well. So this is an entanglement monotone. It's a genuine measure of entanglement. OK? And it seems like a very reasonable one, right? Because it says this is an operational, very operational quantity. It says how much entanglement do you need to make this state? How much pure state entanglement do you need to make this state? So we're kind of building on the pure state case where we are comfortable with our notion of entanglement. OK, unfortunately, it has some issues. And so one of them, a big one, is very similar to the problem we saw with the coherent information, which is that it's not additive. And in particular, if you have two bipartite states, rho AB and rho AB prime, and you try to calculate the entanglement of formation of this tensor product, well, for one thing, you can easily see that it's less than or equal to the sum of these. Why is that? Well, you can make them separately. Separate protocols like this. And then the entanglement entropy of a tensor product is the sum of the entanglement entropies. So you'll get this if you kind of make rho AB using one protocol and rho AB completely separately with another protocol. But the thing is, there might be better ways to do this. And in fact, we know of cases where there are. In fact, we even know of cases where that's true when rho AB and rho AB prime are the same. So making two copies of the state rho AB can be cheaper than twice making one copy. You kind of get a discount for buying in bulk. And so the upshot is that this entanglement of formation is not additive. In this case, it's sub-additive. And so one way around that is to do the same thing we did with coherent information, which is to say, well, OK, what we're going to do is we're going to take the limit as n goes to infinity of kind of the average. And so that's something called the entanglement cost. And it's the regularized entanglement of formation. OK? But of course, once again, we have this limit as n goes to infinity, which means that it's not something that's really calculable. I was going to say easy to calculate, but actually, we don't. I think for the quantum capacity and this, we don't even really know that they're computable. I don't think most people believe that they're uncomputable, but we don't have a proof that there's any procedure of any length to compute these. OK? So any questions about entanglement of formation or entanglement cost? OK, so in that case, let me move on to another measure of entanglement. And so this is called the distillable entanglement. So this one I'm not going to write down a formula for because it's a little complicated and there's some variations. But the basic idea is, so in this case, we were using, we were looking over all protocols to make that state out of entangled pure states. So in this case, I want to go the other way. So the distillable entanglement is the max number of EPR pairs, 0, 0 plus 1, 1, that we can get from this bipartite mixed state using an LOCC protocol. OK? So this notion of distillable entanglement is actually closely related to quantum error-correcting codes and to the quantum channel capacity. Why is that? Well, here's one kind of distillation procedure you could do. We have these rho AB, which we can think of as imperfect EPR pairs. And so what we could do is we could do teleportation through them. We could send quantum states from Alice to Bob using LOCC by using each rho AB instead of an EPR pair. Okay? Now, of course, what Bob gets out of this other end is not going to be the state that Alice sent, because we're not using an EPR pair. We're using this other entangled state. But we can think of it as the output of a noisy channel. Right? It'll be somehow related, depending on what the state is, somehow related to Alice's state, but there'll be some errors in it. Okay? And if we then instead of before we teleport, we use a quantum error. Alice encodes her qubits in a quantum error-correcting code, and then teleports them through. Then Bob can do some error correction and decode the states. And depending on how close this rho AB was to a real EPR pair, it's reasonable that in some situations Bob would in fact be able to get Alice's state. Okay? So that's one way you could use this in terms of error correction. But moreover, I can use that same procedure then to make actual EPR pairs, right? Because the qubits that Alice is sending to Bob could be half of an EPR pair. Right? So when we go through this procedure, Bob decodes. What he's getting out is then half of an EPR pair. Now, in order to make this notion of distillable entanglement precise, you want to say something like it should only be true to high fidelity. What fidelity do we want? Stuff like that. And there's a couple of different variations of how you want to do that. They all come out to basically the same thing in the end. But the upshot is that an error-correcting code can give you a distillation protocol. Now, it's also true that if you have a distillation protocol that only involves Alice talking to Bob, classically, that gives you something that's similar to a quantum error-correcting code. If Alice talks only to Bob, this is called a one-way protocol. And this is kind of essentially the same as a quantum error-correcting code. And so it turns out that the distillable entanglement, so if you look at the state rho AB, which is formed by applying the channel, noisy channel, to a maximally entangled state, then the one-way distillable entanglement from rho AB is basically the same as the channel capacity of this channel. It depends on some property of the channel, whether that's actually true or not. But for many channels, that's true. Okay? But you also have the possibility of a two-way distillation procedure. When Alice and Bob talk to each other. And it turns out, so this is called the rate at which you can do this in the asymptotic limit of many copies is called Q1, the one-way capacity, and this is called Q2. And it turns out that Q2 is greater than Q1, at least in some cases. And notice that if you can distill EPR pairs, then you can use teleportation to send quantum information. So if you have that ability to talk back and forth, then this is actually a better way to communicate for Alice and Bob than just using an error-correcting code. Now, obviously, if you want to store it for some amount of time, then you don't have that ability to talk back and forth. The future can't tell the past what happened. But in an actual communication scenario, frequently you do. OK? So the distillable entanglement, let's call that ED. So the distillable entanglement always has to be less than or equal to the entanglement of formation. Why is that? Well, suppose that it was not. Suppose that the distillable entanglement was greater than the entanglement of formation. Well, then, what we could do is we could take some entangled pure states, appropriate ensemble of entangled pure states, and use them to create the state rho AB. And then we could use this distillation procedure. And what we'd get out would be EPR pairs that were more entangled than the states we put in. Okay? So that would be something that would be increasing the amount of entanglement in the world, well, between Alice and Bob, which we know is not allowed under LOCC. Okay? So it always has to be less than or equal to. And in fact, there's definitely cases where it's less than. In fact, there's cases where EF of rho AB is non-zero, but you can't get any you can't distill any entanglement out. And this is called bound entanglement. You have to put entanglement in to make the state, but you can't, and once you've done that, you can't get it back out again. Okay? So this is also a kind of very sensible operational thing. It's a task that we often want to do. It's different from the entanglement of formation, so that immediately tells you that there's not a unique good measure of entanglement for mixed states. But it also has the same problem that it's very hard to compute, right? You have to optimize over LOCC protocols, even for just a single instance. And it's not additive. It's super additive. And that means that you should maybe look at the regularized version, where you take the limit as n goes to infinity, which means that you don't even have any way to compute it in the regularized limit. So again, it's something that's very hard to compute, even though it has a good operational meaning. So let me show you one more measure of entanglement. Oh, yeah, so let me point out in answer to your earlier question. So this is a case, right, where it's 0 for some non-separable states, but we still think it's an interesting measure of entanglement.
Does formation have the if and only if?
Yeah, I think so. And in fact, it turns out that, again, with some additional assumptions, that kind of any reasonable measure of entanglement is between these two. So these are kind of the upper and lower bounds of the entanglement on the state. OK, so one more measure of entanglement. And this one is not so operational, but it is easily computable. So it's kind of the flip side. And so this is called the negativity. So this is the partial transpose. So if we have, again, think of maybe the 2-qubit case. You have a 4-dimensional density matrix. And as when you took the partial trace, you're going to break it down into 2 by 2 subblocks. And then we're going to take the transpose of each of those subblocks. In this case, I guess I'm taking the transpose on A's side. So the subblocks should be indexed by A's values. And if you start with a tensor product state, then that's just what you're getting is the transpose. So a tensor product the partial transpose on Alice's side is just rho A transpose, tensor rho B. And density matrices are Hermitians, so this is still a valid. It's not the same. It's the complex conjugate here, but it's still a quantum state. OK? And then if you have a separable state, well, this distributes over the sum. The transpose distributes over the sum. So even for separable state, you're still getting a quantum state. But on entangled state, it might not be a quantum state. And so, for instance, if you calculate the partial transpose on the EPR pair, 0, 0 plus 1, 1, you'll see that it has some negative eigenvalues. And then the negativity is the sum of the absolute values of the negative eigenvalues of that state, of that non-state, that matrix. OK? So let's see. So it's 0 for separable states. I argued that already. It's non-zero for some non-separable states, although it turns out not for all. So it's not faithful. And it's invariant under unitaries because yeah, that's a little less obvious. But unitary is a change of basis. It will affect what the partial transpose does, but the eigenvalues don't depend on that. So it turns out that it doesn't matter. I guess it's also maybe not so obvious that, well, OK, it's not too bad to see that it doesn't depend on which side we're doing the transpose. right? If we do the transpose on Alice's side versus Bob's side, well, that's equivalent to doing transpose on the whole thing, up to doing transpose on the whole thing, right? Which, again, takes the whole thing from one quantum state to a different quantum state, but a very closely related one. And so what is obvious is that if you take the transpose on Alice's side, that doing unitaries on Bob's side is not going to change this, right? Because that's kind of doesn't really affect anything. And if it's the same as doing the transpose on Bob's side, then you can see that unitaries on Alice's side don't matter either. Let's see. So I guess it's not completely obvious, but it turns out to be true that it's non-increasing under LOCC. And so this is an entanglement monotone. And the nice thing about it is it's really very easy to calculate, right? Because if you can just write down the density matrix, do the partial transpose, there's no optimization that you have to do over LOCC protocols or anything like that, and you just calculate it. It's just completely formal and straightforward. The bad thing is it's not really closely related to any kind of operational quantity that I know of. So it's unmotivated in that sense. The main motivation is that it works and that it gives you value. So I should say that the partial transpose is one of these examples of a map that's positive but not completely positive. And that's really what we're using here. It happens to be a particularly nice example of such things. And I believe the negativity is also additive, where these other quantities were not. So that's another nice property of it. And because it's not faithful, we can derive another nice quantity from that. We can take a state where the negativity is 0, but it's not a separable state. And then we immediately know, first of all, that the entanglement formation is non-zero because it's not a separable state. But the distillable entanglement has to be 0. How do we know that? Well, suppose we have some distillation procedure for this state. We take this state, we turn it into EPR pairs. EPR pairs have non-zero negativity. And negativity can't increase under LOCC. So we can't go from a 0 negativity state to a non-zero negativity state, so there couldn't be a distillation procedure like that. So it must be that the distillable entanglement of this state is 0. And so therefore, a state that has this property that the partial transpose, the negativity is 0, is a bound entangled state. OK? OK, so I'm well over time, so let me end there. Are there questions? OK, so I'm done, but you're not done. Remember, you have a tutorial today and I guess a homework assignment.
Let's thank Daniel.